All right, so yesterday we talked about solutions, okay? This is one type of mixture. We talked about the difference between a mixture and a compound. Some of the terms we talked about with solutions were solute and solvent, correct? And then I finished up with acids and bases. Who can tell me one word that makes me understand that you know what an acid is? Acids have more hydronium. You're fine. What's one word that you would know that it's a base? Hydroxide. So we're comparing those two to determine whether it's an acid or a base, correct? And we use what scale to do it? pH scale, okay? The pH scale is still here from yesterday. 0 to 14, correct? Where 7 is considered neutral, correct? 14, right, all the way down to 0. 7 is neutral. Above 7 would be considered a base. That's what I said yesterday, right? Below 7 would be considered an acid, right? Yes, no?
Yeah.
Didn't I talk about today, you probably got up and you probably, the first thing you did was pee, right? And hopefully it didn't burn. So you would think your urine is neutral, close to 7, correct? Yes, no?
Yep.
Okay, so with that said, using the pH scale, I can determine whether something's acidic or basic. Like I talked about yesterday, your hot tub or your swimming pool, right? We want to check that water to make sure it's not too acidic or not too basic. I mean, and if it's one, what do I add? The other. If it's acidic, I add a base. If it's basic, I add a acid, correct? To offset or neutralize. I talked about things like Tums. Did I not talk about that or no? Yeah, when you have heartburn or upset stomachs, it calls from the acidity. You take Tums, Rolaids, Mylanta, Pepto-Bismol, whatever, right? That's a base to help settle your stomach. All right, so one of the things we can use along with the pH scale is something called litmus paper, right? It was one of the words I asked you to understand for yesterday's class, but I never got to it. Litmus paper. And I think in your notes I had you write the word red and blue, correct? Yes or no?
Yes.
Yeah. So, when you look at litmus paper, we use it as a way to test things. So, if you look at the screen closely, anytime you use litmus paper, okay, what comes along with it is this little chart. Can you see the color codes? Right? The ones on the left are more red. The ones on the right are more blue or really dark blue. In the middle, they're kind of tan. Okay? So, I can use litmus paper to test things. So, over here, I have 3 clear liquids, very different from one another. There's a couple different ways you can test them. You could drink them, but I wouldn't recommend it. Okay? Because you don't know what they are. Right? Or I can use litmus paper, which is a little roll like this. See the roll on the screen? Okay? It's a little roll, and what I can do is dip this in, and you should see a color change. So when I dip the first one in, you can see the color change. Would it fall on that side of the scale? Yeah, so what would I call that? That's a base. What does that mean? That means I have more hydroxide than hydronium, correct?
Yeah.
Yes, no?
Yeah.
Okay. Yeah, that's straight hydroxide that I put it in. Would you want to drink that? No. Because what do bases do? They burn, correct? They burn slower. Okay? What did I give yesterday as an example of a base that you might have used today? Shampoo or soap. Okay? Cleaning products are made of bases. Okay? Now, the one on the right, if I dump it in, you can see the color change. Falls over here, doesn't it? Yes, no?
Yeah.
Yeah. That's an acid. What does that mean? I've got more hydronium than hydroxide. So I fall at the bottom of the pH scale. So I'm on the left here, closer to 2 or 3. What?
Would you like us to know the what's it called? The equations for?
That would be useful. Okay? So clearly now the third one, where do you think it's going to fall? If you had to guess. Somewhere in the middle, right? Yeah. So if I dip it in the third one, there's really no color change, kind of stays beige or tan. It's a little bit better on a TV than on this projector. So that's going to be closer to 7. Any idea what I might have put that in? Not just any old water. Distilled water. Do you know what distilled water is? Do you know what distilled means? Ah, close. It's different than purified. Distilled means I took all the ions out. Didn't I say H3O and OHs occur naturally in water, which allows it to transmit electricity, which makes it conductive? If I take out the ions, that's called distilling it. Why would I want water with no ions? So I can do experimentation, right? I put water or distilled water in batteries to keep them longer lasting. Okay? What? Have fun. Check the Schoology. Get to watch today's video. Who were you around?
Pete.
Who?
Peter.
Rosa? Right. You know what's even funnier? Guess who sits close to him for 3 straight periods? Right. You think they care about me? Me neither. Sorry. Why would I want to be out of here? I enjoy seeing your pretty little face, Xavier. I know you want me gone. It's okay.
See you, Mr. Ricker.
See ya. Have a good one. You'd like that, Zavi. Mr. Riker quarantined for 2 weeks now. I don't have to see his ass. Okay, so do you get this test with litmus paper?
Yeah.
Okay? So I can use a simple test. This is how you can test your hot tub. This is how you can test your swimming pool. This is how you can test anything, right? I guarantee you, like I said, if you got up this morning and the first thing you did was urinate, right, and it didn't burn, it's going to be somewhere here probably, neutral, right? New word though is distilled. It means to take out any ions with charges, okay? And we use water for that. Now, would distilled water be good for you to drink if you're playing a sport? No, that's why you drink Gatorade and all the other energy drinks, because they have electrolytes. Electrolytes have charges. You want those because that's what allows your body to send messages to and from your brain, right? To your muscles. It's those electrolytes that you want. You can get them from regular tap water because they're already there. I told you that. But distilled water, they're removed. Okay? So you're not as beneficial or getting as much benefits from distilled water as you would regular water. Cool? We good on acids and bases? All right, so going back to our list. Okay, going back to our list or our flow chart, you can see that's just one type of mixture, right? A solution. And I gave you kind of 2 examples, solute, solvent, acids, and bases, right? Now, there's 2 other types of mixtures. What are they called? Suspensions and colloids. Good, you can read. Okay, now, do you know the difference? Well, probably not, but you will hear in about 5 minutes. What can you tell me about the 2 things in a solution? What was the first example I gave you of a solute and solvent? Do you remember?
Salt and water.
Salt and water or Kool-Aid? Did I use the Kool-Aid example?
Yeah.
Sugar and water. Okay. So, what happened to the sugar? It got dissolved. Why was it able to get dissolved? Because it was small. Now, a suspension's a little different. Do you know what a suspension is on a car? It keeps you from sinking and hitting the ground. It suspends you up, right? Higher suspension, you're sitting higher off the ground, right? What do we use to keep your car suspended? Do you know what those things are called? They look like springs. They're called shocks, right? Shock absorbers, right? Okay? So, suspensions elevate stuff, correct? Okay, so here's a good example of a suspension. How many eat salad? Have you ever had Italian dressing? What did you do to the bottle before you poured it on your salad? What'd you do? Right? You shook it, right? Okay. So, you shook it. Why'd you shake it? All this good stuff was at the bottom, right, Nolan? Correct? It settled to the bottom. Do you shake your orange juice? Do you shake your milk? They're examples of suspensions too, because the good stuff settles to the bottom. But particularly that Italian dressing, you want all those herbs, you want all those seasonings that sunk to the bottom. You don't want just the oil and the liquid at the top, so you shake it. And temporarily, what do those particles do? Aren't they suspended inside the liquid?
Yeah.
But if I let that bottle sit for 2 minutes, where do they go? Back to the bottom. Why don't they dissolve? Say it again. They're too big to dissolve. Absolutely. Liam? Right. So, solutions are over here. Those particles are so small, they get dissolved. They don't go away, they just disappear. Right? Visually. They're still there because you still taste the salt and the sugar in our example. Right? The Italian dressing's way over here because the particles are so big. So what's the definition of a suspension? It's two things act like a solution, but they don't dissolve because they're too big, so they settle over time. So when you look at my definition in my notes, a suspension is a mixture where the particles, like a solution, are spread throughout, but because they're too big, they don't dissolve, they settle over time. Do you follow me? Okay, how many have ever been to the ocean? Probably a lot of you, right? You ever catch water in a pail that comes in a wave? You ever play in the ocean, and then when you're done, you go home, you take your bathing suit off, you got sand in your drawers? Right? Where's the sand? The sand's in the damn wave when you come in, right? If you take a pail or a bucket and take the water from a wave that comes in, and you fill up that bucket, it'll look brown and murky, but in about 4 minutes, what'll happen? If you let that bucket sit. All the sand will sink to the bottom, and the water will be clear. That's another example of a suspension. Those sand particles are too big to dissolve. Now I'm going to give you one very important suspension that's in your body. Your blood. Your blood is another example of a suspension. You think about it. We know blood transports nutrients to and from the body parts, correct? Takes waste products to where they want to go and takes nutrients to where they want to go. It's the highway system, okay? Think about the different parts of blood. Who can give me some different things you find in your blood? Zavi. Okay. Red blood cells is what I'm thinking.
White blood cells?
White blood cells is another thing. Would you consider those two things solids? Yeah. Plasma, what's it mostly made up of, Puda? Solid or liquid? Liquid, good guess. That liquid plasma is mostly what type of liquid? What's most of our body made of? So it's mostly water. Plasma is mostly water. And it's inside that plasma where the white blood cells and the red blood cells flow and move. We know the job of white blood cells. What do? They help fight off foreign invaders. They help you when you get sick. So what happens to your white blood cells when you're sick? Do they go up or down?
Up.
They go up in number, don't they? Anybody know the job of the red blood cells? They're the things that carry the good nutrients to where you want them to go. Okay? So, you've got solid white blood cells, solid red blood cells. You got the liquid plasma, right? That's the makings of a suspension. The blood cells don't dissolve. They'll settle over time. If you're sick, sometimes you go to the doctor, they're going to draw blood. They draw blood, put it in a test tube. Over time, those solid red blood cells and white blood cells are going to do what in that test tube? Fall to the bottom, just like what in the Italian dressing? The herbs and the spices. That's how they separate, so they can determine how many white blood cells and how many red blood cells you have in your body. If your white blood cell count is way up, that's a sign that you're what? Fighting off a sickness. Okay? So blood is an example of a suspension. Okay? And I say that here in my notes. But the big thing is, why do they settle over time? Why do they settle over time? Too big to dissolve. They're too big to dissolve. They're large compared to the solute in a solution. Okay? So you've got solutions over here where they dissolve. They're small enough to dissolve. You got suspensions over here where they're too big to dissolve. Where do you think the third mixture falls? Somewhere in the middle. What's that third mixture called? It's called a colloid. Star colloid. It's the most important mixture in regards to living things. It's the most important mixture in regards to living things. Read those notes there on colloid. What's the one example that you're going to have to know in STAR? What?
Particles do settle over time.
Yeah, but no, what's the example of a colloid that I give you?
Cytoplasm.
Cytoplasm. Where is the cytoplasm? It's everything that the cell's made of. Cytoplasm is a colloid. That's why it's the most important mixture. Because every living organism is made up of a cell or multiple cells. And the main substance of cells is cytoplasm. Now, what are the two different states in a colloid? The liquid state and the solid state. Right? What do I call the liquid state? Sol. Right? Don't ask me why. Because you would think sol would mean solid. I didn't make up the name. The gel is the solid state. The sol is the liquid state. The best way I can explain a colloid is to give you the example of Jell-O. Y'all know what Jell-O is? You know how Jell-O's made? You get the little box, it's got the sugar packet in it. You mix it with what? Water. The water turns the color of the sugar packet, right? Then what do you do with it? Throw it in the fridge, right? What happens to that liquid Jell-O? Does it turn kind of semi-solid? Does it take the shape of its container? Can I empty it out of the container and will it still maintain its shape? Yeah. Is it very solid? No, you could probably put your finger right through it, correct? But it does maintain shape. But it's a very semi-solid, correct? If I heat it back up, will it turn back to a liquid? Absolutely. So can it go back and forth from solid to liquid? That's what cytoplasm can do. And that's important for a cell. Because when you take an example of a cell, right? You have the nucleus in the center, right? You have all these organelles, right? The mitochondria, the endoplasmic reticulum, right? The lysosome, which are all things we're going to learn about next chapter. They have to do their job. In order to do their job, they have to have the ability to do what inside the cell? Okay. One of the things that happens inside a cell is the elimination of waste, right? Okay? How do you get rid of your garbage at home? You put it out to the curb and somebody comes and grabs it, right? What happens if the garbage men had no truck? They'd have no ability to move. Would they pick up your garbage? No. So do these organelles have to have the ability to move within the cell? Is it easier to move in the solid state or the liquid state? The liquid. So the sol of the cytoplasm allows for movement within the cell. What does the solid gel state do? It gives the cell its shape. So in other words, this cytoplasm is sometimes a solid, a gel, and sometimes a liquid, a sol. Why is it important to be a sol sometimes? So that things can move. Why is it important to be a gel? So it helps maintain the shape of the cell. That's what makes a colloid, to me, the most important mixture. Because every cell is made of cytoplasm, and cytoplasm is the best example of a colloid. It goes back and forth from a solid to a liquid, to a liquid to a solid. It's constantly changing, just like Jell-O would be if I took it out of the fridge and put it in the fridge, out of the fridge and put it into the fridge. Does that make sense? So, when you talk about the three mixtures, you've got solutions where the particles are really, really small and they do what? Dissolve. Then you got way over here, suspensions where the particles are really, really big and they do what? Settle or sink to the bottom. The colloid somewhere in the middle where sometimes they dissolve, sometimes they don't. Sometimes they're a liquid, sometimes they're a solid. Sometimes they're a sol, sometimes they're a gel. Do you get that or no?
Yeah.
Okay? Fair enough? Makes sense? Do you understand the three mixtures? That's what I need you to know. Okay? Now, if you look at your vocab sheet that I had you turn in on Tuesday, or that I gave you back on Tuesday, I'm pretty sure I got most of the terms pretty much covered as of right now, with a few more remaining. Here are the few more remaining. They center around energy. Energy is basically the ability for something or someone to do work. And when you talk about work, you're talking about movement. So energy allows you the movement of mass. Okay? Without the movement of mass, you don't have any work taking place. Now, who can tell me different types of energy? I'm using one right now to communicate to you. What type of energy am I using right now to communicate to you?
Mechanical?
No. I'm using sound energy, my voice. Okay? Mechanical is a type of energy. Give me a way in which you used it this morning. You used mechanical energy a lot of ways this morning. What? To move to move your body to turn on the shower. You drove in a car, I bet you, that mechanically brought you here. The wheels spun, the pistons in the engine moved to spin the wheels. That's where the pistons got their name, right? We're the Motor City, right? We build more cars than any place, right? What's the motor made of? Pistons that move up and down that make things move within the car, like the tires spin. That's mechanical energy, okay? You used mechanical energy when you got out of the car and walked your butt into school today. I'm using mechanical energy right now to move around. Some of you are using it to write, okay, and take notes. So mechanical energy, sound energy. We're using light energy right now, okay? We're using heat energy. You can hear the heat from the ducts, right? Yes, no?
Yeah.
Okay, so there's a lot of different forms of energy. And I list a few there in my notes. Okay? One of them is chemical. Give me the two ways in which you use chemical energy today. Give me 2 ways in which you use chemical energy today. Yeah, you ate food. You're breaking it down to release the chemicals from the food to create energy. What do I call that process, and where's it done in your body?
Digestion.
The process of breaking it down is digestion. But the process of using the chemical energy or making the energy from the chemical stuff you ate, where's that occur and what process is doing it? We've already learned this. Where do you make energy in your body, guys? Where in the cell do you make energy in your body? The mitochondria, thanks. What process occurs in the mitochondria to give you your chemical energy? I'll give you a hint. The chemical energy's name is ATP.
Oh, respiration.
Thank you. It's called cellular respiration. What do plants use? Photosynthesis. You guys are killing me, right? You guys are becoming slow as my first hour. Okay? Just saying. Okay? You guys learn things for the day and then forget it. What else did you use for chemical energy today besides food, David? You were good. Give me something else, someone. I said you rode in a car. What did the car use for chemical energy to make the mechanical energy of the engine go? Gasoline, right? The fuel that you put in the car is chemical energy. Okay? So those are different forms of energy. Now, what are the 2 basic types of energy? Any idea? If you could see, some of you, seriously, it's like, Letitia, I want to put a mirror underneath your mouth to see if you're still breathing. If you're alive. And you're a good student, dude. Just the look, it's hard to get over. Right? Potential and kinetic. Potential and kinetic. Okay? There's a difference. Potential energy and kinetic energy. Okay? Now, if you look at the definition of potential, it's called energy of position or stored energy. Correct? Okay. So, here's a cliff. It's 100 feet. Here you are after I gave you your first quarter grade. Right? You're standing there, looking over. Is that kinetic or potential? In regards to the ground, it's potential energy. It's all potential energy. 100% of it. Right? 100% of it. Okay? Yes, no?
Yeah.
Okay. You jump. What does that potential energy do?
Release.
It starts to go down. But what goes up? Kinetic energy. So let's say here you're at 75 feet. What's your kinetic energy and potential energy? My potential energy in regards to the ground is 75%, but my kinetic energy is now 25%. Does that total the original 100? Yeah, because whatever I start with, I got to finish with. Okay? As you fall, do you pick up speed? Yeah, due to gravity, correct? Yep. When I get here to 50, what's my potential? 50. What's my kinetic? 50. Down here at 25 feet. I'm now, in regards to the ground, I'm a lot closer, so my potential energy is a lot less. But hell, my kinetic energy is way up. Do you see how that works? Potential is energy of position based on the top of the cliff or the increments down. Kinetic energy is energy of motion. The more movement, the what? Greater the kinetic energy. Do I have more movement down here? Yeah, I've accelerated that many feet due to gravity. Where's my maximum kinetic energy? Right before you hit. Because when you hit, what do? Stop, and everything goes right back to what? 100% potential energy. Does that make sense? Yes or no? Do you understand the difference between potential and kinetic energy? So, does my car have potential energy right now, my truck? Hell yeah, it does. It's sitting there waiting to be turned on, and I got an engine in there that can make it go. Right? How many brought a lunch? How many have an apple or a banana or a piece of fruit in there? Does that have stored energy? Absolutely, just waiting for you to break it down and release the chemical energy. Right? How many have a calculator sitting in the book bag that has batteries in it? Right? If it's turned off, does it have potential energy? But the minute you turn it on, what does that potential energy start to do? Turn into kinetic energy because you're using it. Does that make sense or no? You understand the difference between the two? Okay. Fair enough? Now, how many know the different phases of a substance? Solid, liquid, gas, right? Take water, for example. The solid is known as ice, right? What do we use it for? To cool things? We use it to skate on things, right? Yes, no?
Yeah.
If I heat up ice, what does it turn into?
Water.
Water, right? We drink water, correct? We swim in water, correct? Right? If I really heat the water, I change it to steam and I can power things, like make a turbine spin and generate power to turn lights on. That's what a nuclear power plant does. It uses steam, water to turn to steam, but it needs energy to make the water boil to turn to steam. That energy is nuclear energy that we use, okay? So that's a gas. Which has more movement, a solid, liquid, or a gas?
Gas.
A gas. So it has the greatest or the least kinetic energy? Greatest. But it has the least what? Potential energy. A liquid, does it move a little bit less than a gas? Does it have a little more potential energy, but a little less kinetic energy? Ice, a solid, has the most potential energy, but the least movement, so it has the least kinetic energy, correct?
Yeah.
Make sense or no?
Yeah.
So think about this. In regards to potential energy, liquids have more potential energy than gases. Just think about it. If I throw a balloon at you, would that hurt? Maybe some of you, I don't know. But if I threw a water balloon, could that hurt a little more than a regular balloon? Yes. What if I threw a water balloon where the water was frozen into ice? Would that really hurt?
Yeah.
Probably. So, when you talk about solids, liquids, and gases in relationship to potential and kinetic energy, do you understand the difference? Solids have the greatest what? Potential energy. Gases have the least potential energy. Solids have the what? Kinetic energy. Least. And gases have the greatest kinetic energy. Does that make sense? So we use potential and kinetic energy as a way to look at states of matter. How many can explain what a chemical reaction is? Well, it's real simple. I have it underlined here. Right? Basically what you have happening is you have ingredients which we call reactants. And they turn around and make what are called new substances, which we refer to as products. Right? In order to do that, they have to have bonds broken and new bonds formed. What are the only two reactions I've given you in this class thus far this year? Photosynthesis, good, and you said it, respiration. I break bonds to make new bonds. That's what a chemical reaction is. The breaking of bonds to form new ones. Reactants make products. I have two final things to talk about. Make sure you bring the notes from biochemistry that I had you print for the other day, and make sure you bring that new vocab. The vocab that was graded. Wipe off your desks.